Reducing fractions, and we're actually going to use some of the numbers that we used in the previous lecture. But not yet. We have to discuss what we mean by reducing fractions. Okay. Every fraction can be written infinitely many ways. That's a lot of different ways. Every fraction can be written infinitely many different ways. So I'm going to use my blue pen here. Just so I could have a little color out there, you know. Some people like color. Okay. And I've taught, this is another question. Every time I've taught this, I get the answer I'm not, so far I've gotten the answer I'm not looking for.
Okay.
But I do get a correct answer. But it's not necessarily the answer I'm looking for. And let me just throw all the ink in this pen out here on this. Okay. All right, here's the question. And you know what I'm going to ask. What fraction is that?
1/2.
1/2. Okay. Now, this is the $1 million question. What fraction is that?
Still 1/2.
Still 1/2. Oh, see? 2/4. Both are correct. Okay. What fraction is that?
1/2. Or 4/8.
1/2. What fraction is that?
1/2 or 8/16.
1/2. Oh my gosh, I'm going to kill myself on this one.
Why are you doing this?
What fraction is this going to be?
Something. It'll be 1/2.
1/2. Good. You get the whole point here. It's 1/2. It doesn't matter what the other fractions are. The point is this is 1/2. I could do it this way too, and it'd still be 1/2.
Mm-hmm.
And it wouldn't be too hard to figure out what this is. Because this has 4 boxes, and there's 16 there, so there's 16 total boxes, so 16 times 4 is 64, so this fraction is 32/64, or 1/2. Okay. Starting here and reducing this is reducing fractions. Starting here with the complicated fraction and breaking it down to the simplest form is 1/2. And we call this the simplified form. Because it's simple. All these crazy extras, that's not simple. That's why we reduce fractions. So we can use small, pretty numbers. Simplified fraction. Okay, so this is the fundamental that's a common word today, fundamental. The fundamental principle of fractions. One that a lot of people... Okay, so if I have a fraction A over B. Yes, I know, those are letters, but they're variables, they represent numbers. So it can be any number A and any number B. Well, almost any number. B can't be 0. B can be A, B can't be 0. You can't divide by 0. So the fundamental principle of fractions is if I multiply the numerator by a number C and the denominator by a number C, I end up with the same fraction.
Okay.
Okay.
I'm with you.
Now, there's 2 ways that this helps us. And also notice that 1 over C and 1 over C, like this, that means if you divide the numerator by C and divide the denominator by C, you would still get the same fraction. Okay. 1 over c is just another number. Okay, so why do we want to know this? This fraction here, if we have, let's go real simple here, 4/6. Okay, we know that 4 is 2 times 3, and 4 is 2 times 2, and 6 is 2 times 3. Do you see where the c is?
Yes.
c is 2. Okay.
Mhm.
It's also 1. You can factor that out. So 4/6 is 2/3. Now it just so happens that the number that the factorizations that I put up here are the prime factorizations. If you use the prime factorizations to reduce fractions, you'll never get it wrong. Okay.
Okay.
Just be careful. This rule only applies for multiply. So let me do it again. 2 times 2
It only applies for
over
what?
multiply.
Okay.
You can only cancel, I hate that word, you can only factor out that 1 if it's all multiply. If it's 2 plus 2 over 3 plus 2, like that, and you can't do this because it's plus. It don't work for plus. Only works for multiply.
Okay.
Okay, because you can what you're doing is you're factoring out 1. Okay? So we can use this principle to reduce fractions, and we can also use this principle to build up fractions, which we'll do when we add and subtract them later. Okay, so let's reduce some fractions, and let's use some prime. And these are going to be proper fractions. The principle works for improper fractions as well, of course, but. And mixed numbers, but we're just going to use proper fractions, and we're going to reduce 52 over 66. Okay, and if you were taking notes, you'd have these prime factorizations already. Oh, look at that! I was taking notes. Okay, so this is one way. Both of these methods involve prime factorizations. There are other ways to do this, of course, that are a little quicker. But if you struggle with reducing fractions, you can always step back to this method. I'm going to go over some other ways of doing this. With the same number, we're going to reduce this 3 different ways.
Okay.
But we're going to do it the prime factorization way first, which is the way I recommend doing it, until you get enough practice that you can do it in your head and go, oh, well, that's 13 over 33, or whatever it is, 26 over 33. Okay, so it's 2 times 2 times 13 is 52, and 66 is 2 times 3 times 11. Okay, and you can see what we could take out there, right?
The first set of 2s.
First set of 2s. Now, just so you know, they don't have to be on top of each other. If the 2's over here and you could still go like this. That's still 1, okay?
Right.
So don't be confused by that. Then we multiply what's left. 2 times 13 is 26, and 3 times 11 is 33. One way of doing it. Prime factorization way. Second way. If you see, and a lot of people miss little factors on this one, then that's why when the numbers get really, really big, I don't recommend this. When they're small, then yeah, most of them are divisible by 2. There's only 3 numbers that aren't less than 100 that aren't divisible by 2, 5, and 3 that aren't prime, right? So the only hard ones you're going to really struggle with are 91, 77, and 49. Okay, so you can see that both of those are even, right? The numerator and the denominator are both even.
Correct.
So divide both of them. Divide it out. 52 divided by 2 is 26, and 66 is
33.
33 divided. 66 divided by 2 is kind of chalk. It's 33. Another way of doing it. Same answer. Now in this way it's faster, but maybe you miss another factor somewhere else. The other thing you can do, and it still uses prime factorizations, is that's to find the greatest common factor. And we can already see what the greatest common factor is. What's the greatest common factor?
2.
2, and then divide both sides by the greatest. It's the same thing, okay? So in other words, some people teach this method, some people teach this method, some people teach this method. They're all the same. The only thing is, whichever one you're comfortable with is the one that you should do, okay? If there's numbers are small enough, this is the method I use, and I'll reduce them in my head. But if you're not comfortable and you don't know that, let's say reduce 35 over 10,000. Why am I using that one? Because that's the number I picked last time, right?
Mm-hmm.
Okay, this one's easy, actually. But, okay, 35 is 5 times 7. I'll do it that prime factorization. I'll give that one.
Okay.
Or if you want to go through it, is it divisible by 2? No. Is it divisible by 3? No. Is it divisible by 5? Yes. How many times? 7. That's how quick that is. And I'll just refresh your memory that is the prime factorization of 10,000. And you can see that this crosses out there, and one of these 5s go. So what's left? 7 over 2,000. Okay? You need to see that 10,000?
No, I trust you.
Well, look, there's 2 times 5, 2 times 5, and 2 times 5. That's 10 times 10 times 10, right?
Right.
Which is 1,000.
Times 2 is 2,000.
See? You can do it. I have faith in you. Okay. Should we do some more examples?
Sure, let's do one more.
I have a few.
Okay.
Okay, we're going to keep these small, though. Use any method you want.
Okay.
All right. Are these both divisible by 2?
No.
Are they both divisible by 3?
No.
Are they both divisible by 5?
Yes.
Okay, so 10 divided by 5 is 2, and 15 divided by 5 is 3. Now, one of the things that's great is if you end up with 2 prime numbers, you're done automatically. There's no way you can break those down. So 10 15ths is 2/3. Okay, here we go. We can. Was that you or me? Do, 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 do. I think it was me.
Okay. So I didn't hear anything.
Oh, it was me. 42 divided by 24. Now, do you want to do the prime factorization method, or do you want to do this quicker method here, because these are all small numbers, or do you want to do, what do you want to do?
Well, do 3.
Let's do the prime factorization method. Why not?
Okay.
Okay, 42 is 6 times 7. Right?
Okay.
7's prime, 6 is 2 times 3. So 42 is 2 times 3 times 7. 24 is 8 times 3. 3 is prime, and I'm coming down to the bottom here. 8 is 2 times 4, and 4 is 2 times 2. So, 2 times 2 times 2 times 3. Yeah?
Right.
So we got a 2 there and a 2 there, and a 3 there and a 3 there. So what's left? 7 over 4. Now, here's a little trick. This is improper, right?
Yeah.
Why is it improper?
Because the numerator is larger than the denominator.
When you reduce it, your answer better be improper too, or you're in trouble. Just a little hint there, okay?
Okay.
So, I don't know how you flip it upside down or whatever. It could happen. All right. 13 over 15. let's use the prime factorization method on this one because this one's not too
Okay.
bad.
Well, 13's already prime.
13's
so.
prime, and 15 is 3 times 5. Well, what happens if you can't cross anything out?
Then it's already done.
It's already reduced. Very good. You're so smart. Nine over 45. Last one.
That one's going to be a whole number.
Huh? Oh. See, this one's a tricky one. What happens if you run out of numbers? See, I wanted to do one of these like that. 9 is 3 times 3. And 45 is 9 times 5. Right? Right?
Yes.
Okay, so this is 1, and this is 1.
Mm-hmm.
So 9 over 45 is 1/5. If you run out of numbers, you factored out a 1.